Right, so we're looking at the homework here. So I don't know if I made it real clear last time, but the 6 problems are all due Thursday. So 271 through 276 are due on Thursday. And also there's a new version of 271, 2, and 3. If you have the newer book, which is, I think the newer book says 2000. It doesn't look too good, does it? I guess we better get that down. There we go. All right, so your book should say, I think it's 2019 fall, and then it's got a B after it. That has the correct problems in it. If it doesn't, you either need to get a copy here in class, which I handed them out, or you need to go on Moodle, and I've got them posted in Moodle, okay? And so 271 should look like this. All right. So these, the first 3 are based on coming up with a free body diagram using trigonometry and getting the thing broken down so you can take moments about a pin joint, I think is how the first 3 of them work. Now I'd be happy to go through any of the first 3 you'd like me to. I mean, there's the first one, there's the second one, and then the third one looks like that. And they're all use the same approach, although they're all, of course, different types of problems. Are there any questions on any of those in particular you'd like to go through, or one you'd like to look at? It might be worth a while to go through at least one of them just to kind of get the approach down.
You want to go through the second one?
Second one? Okay, sure. We'll do that. All right, here's the second one. All right, so the deal with these types of problems goes like this. What you want to do first is actually the stuff at the bottom, okay? So I'm going to look at that thing and I'm going to say, okay, I need a free body diagram of that. And then what I'm going to do is I'm going to look at where the forces are applied. The forces are applied at the pin joint right there. Of course, they're applied in this distributed load. And then there's a force right there. Okay, that's where the forces are applied. So that's step 1. Step 2 is to say I've got a pin joint at C. So probably the way I'm going to start this problem is I'm probably going to start it by going sum of moments about C equals 0. That's how I'm going to start that thing. And the reason is there's 2 unknowns there. In a 2D statics problem, you can only have 3 unknowns and be able to solve it. So if there's 2 unknowns at the pin joint, there can only be 1 other unknown on the object. And by taking a moment about C, I'll eliminate the 2 at the pin joint. I can solve for the 3rd. So that's my thought process. Okay. Now, if I'm going to take moments about C, what I want to do is join C to every one of the forces that are applied with X and Y dimensions. That's what I want, because then I can come up with a moment equation pretty readily. Okay? So that's kind of what I'm thinking about when I start looking at this problem. So we good with that so far? We got any questions as to the approach or anything like that? Yeah.
What do you find the angle of 37 to 31?
It's 37. You got 143 given,
okay,
and you're just taking 180 minus that, I think. So yeah, that's probably worth writing down. So yeah, that's that 37 degrees right there. That's coming from the total of 180 for a horizontal line, and then subtract off the given angle, which is 143. And that's where the 37 comes from. Okay. So what I'm going to do then is I'm going to kind of, is there any other questions? Okay, so that stuff you see in the lower left there is all done with the intent of just making a nice clean set of X and Y dimensions from C to where the forces are applied. Okay, I've got the 600 newtons per meter, and that acts over 1.8 meters right there. So if I take 600 times 1.8, that gets me 1,080 newtons. And that will be located at the centroid of that load. Okay, the centroid, being as it's a rectangle, will be half of 1.8. It'll be 0.9 meters. So that's where that distance there comes from. Half of 1.8 is 0.9. All right, now I'm going to go down to point A there. And I know I have an angled force that's normal, which is another word for perpendicular to that ramp. Okay, so the angle of the force is normal or perpendicular to the ramp. The ramp is 29. If I take 90 minus 29, I'll get the angle of that force at 61 degrees. Okay, so that's the angle of the force at A. So when you apply that at A, it's at 61 degrees. Now, sometimes I've seen people make an error and they see that armature and they want to make the force go up the armature is what they want to do. It's kind of a normal, intuitive thing to do, but it's not the right thing to do. The force is normal to the ramp. The angle of the armature there has nothing to do with the force at C. They're totally unrelated things. Okay, so just because that armature goes down at that 37-degree angle does not mean the force has to go up the armature. It's not what happens there. The force angle is governed by the ramp. So 90 minus the 29 gets you the 61 degrees for A. That's how that goes. All right? Now what I want to do is connect C to A with X and Y dimensions. To do that, I'm going to take that armature there, which extends out 1.4 meters at a 37-degree angle. So I do a bit of right angle trig. I go cosine 37, 1.4, and I get the adjacent side, sine 37, 1.4, and I get the opposite side. So I go ahead and put those dimensions right on there, and I put them in kind of an X and Y form so I can kind of see what's going on there. What's happening here now is I've taken that angled bracket and I've basically changed it into X and Y's. So I've got this, as far as I'm concerned now, it does that. Okay? As long as that's a solid, rigid object, how I get from C to A doesn't matter. What matters is the position of A and how it relates to C with X and Y dimensions. Okay? As long as it's a solid, rigid object, the nature of the connection doesn't matter. It's this object could do this for all I care. It doesn't make any difference, all right? All that matters is where's A and where's C. That's all I care about, all right? And I really want to get that point across because, I do these things on AutoCAD. My sketching ability is a little crude on AutoCAD, but you open up a statics book, you're going to see all different things, all different pictures in there. Landing gears from aircraft, artificial limbs, hydraulic cylinders, you name it, you're going to see it in those books. Wheelbarrows, everything else. It doesn't matter, okay? It can be anything. What matters is where the forces are applied and how you connect them together. So get over the sketch is kind of what I'm telling you here. Just turn it into a force diagram and a dimensioned force diagram with the origin at the point you're going to take moments about. Okay? So that's the deal with that. Yeah, question there?
So when you have a 1080 Newton at 29,
Yeah.
from B or A? I mean, C or A?
It's from C. It's from C. Did I bust that? Yep, I busted that. Thank you. Yeah, it's from C. Thanks. Yeah. Okay. All right. Other questions? Okay. So, all right. So I want you to take that sketch and I want you to turn it into what I just drew. Just a right angle bracket with a pin joint at A, a load 0.9 meters, a pin joint at C, a load 0.9 meters from C at 1080, and then this angled load as shown at A. That's really the critical first step. Once you got that, the rest of it's pretty mechanical really to solve it. All right? We're good with that? Okay. Okay, that's just a matter of generating equations. All right. All right, so what you're going to do is you're going to start at C and go to where the forces are applied, and you want X moment arms with Y forces and Y moment arms with X forces. That's how you want to do that. So we're going to go cosine 61 RA. That gets you the X force at A, because I'm going cosine, which is the adjacent side, adjacent to that 61-degree angle. So that's going to get you that force right there. And then what you want is a y moment arm, 0.843. So that's all set up and ready to go now. That's the idea. Now what that's going to do is that's going to undercut under C and come around like that. So that's going to be positive. Okay. You all okay with that? Okay. Then we got sine 61 times RA. That's the y component. That'll go with an x moment arm. That's 1.8 and 1.118 more. So that's 2.918 meters. That'll come around that way, clockwise, so that gets a negative sign. Okay. And then the last one there is right there, 1080 times 0.9. That's going to come around counterclockwise, so that gets a positive sign. We good? We good with that? Okay. Now, once you got that set up, there'll probably be an intermediate step there where you calculated each one of those individually and then work it down to get to 2.14. RA is 972, so RA is 453 up and to the right. That's 61 degrees. Okay. Now, once you've done that first moment equation, you got two unknowns left, but they're in the x and y directions. No more moment equations. They're more complicated, more chance for error. So what I'm going to do next is I'm going to go sum of fx is 0, sum of fy is 0, and solve for rcx and rcy. So, got any questions on that? So that's some fairly complicated little problem, but that's, that covers a lot of what we do in statics, okay? The moments, the forces, equilibrium. And that also kind of gets to that how engineers work kind of thing, okay? Because these are the skills you want to develop, so when you go to work 3 years from now, you're systematic and you just kind of march through things. That's what you want to do, all right? I think I told you I spent a week designing a road intersection about the size of this room. Real complicated, changing grades, crown section to an inverted section, angular change and all that. Spent a week at it, okay? All the little numbers to get the thing to drain properly and all this crazy stuff. Yeah, I was pretty burnt out after that week. But man, one mistake on Monday. Ooh, that's bad news on Friday. And actually there was a mistake. They gave me the wrong base map. Which someone pointed out to me on Friday afternoon, which I wasn't very happy about. But anyway, this is what you want to develop, see, because if you ever seen plans for a pipe gallery, like in a water plant, where you got pipes going up, down, left, right, north, south, east, west, angles, and they can't intersect and they're going over the place. I've seen plan sets for those things, and they are, I don't know what their word is, gnarly. It's, you got to keep that all in your head and work with it. It's difficult, and you got to be systematic about it. Okay. Nowadays they do that stuff with 3D modeling. They used to do it with plan sheets. Now they build an actual 3D model of the thing and make sure it fits and works. But anyway, okay. So that's another thing I want you to learn here. Is just that systematic approach. That's kind of what engineers do. Okay. Step by step. All right. So we got questions on that one? Okay. We're good. And that's kind of the blueprint for the first three right there. That's kind of the method. Okay. good? Everybody got that? Okay. All right. Now the first one, you just have that couple up there. So what? You got a motor up there at A. You're going to take moments about A, right? Because there's a pin joint there, and you're going to want to dimension that thing like that and like that, right? You're going to have this. That's what you're going to want to do with that, right? Are we good with that? So you're going to want to treat that. And then the last one. Is there anyone? We good? We good? Okay. Now this last one is a little bit, it's got two angled pieces. That's okay, you just trig each one of them out. So you want to go like that, and then you want to do the same thing over here. So your goal here then, your finished product that you want to work with so you can get a good free body diagram is to get this thing kind of worked out. Where you've got one thing like that with an X and Y dimension to that point, and then the other one you're going to want is another set of dimensions like this to get to that point, right? So you want X and Y dimensions that go from the point about which you're taking moments, which in this case is A, to the points where the loads are applied. B and C, I think. Yeah. All right. So we got 40 degrees. Now, how long is that first armature coming from A to B? I've got that thing kind of muddied up. 0.6. So what? Cosine 40 times 0.6. Yeah, so 0.460, I guess we could call it near enough. Okay. So that's 0.460. And then you're going to have sine 40 times 0.6. 0.386, and then you're going to go sum of moments. Eventually you're going to be sum of moments about A is equal to 0, and then that's going to be what? So that's going to be sine 15. So here's my thought process on that. Sine 15 times 280, that'll get me the Y component. That's going to go down. That's a Y force. I want an X moment arm with that. They're newtons, right? And that's going to be 0.46 meters. Okay, then I look at that. If that pushes down, that's going to go clockwise. So that's going to get a negative, right? I put the numbers in the parentheses, then I look at the direction. I don't put any signs in the parentheses. That just muddies things. Just put the numbers in there, then I look at the sign after I've done it. And then I'm going to have what? Cosine 15, 280, 0.386, right? That's going to go around clockwise too, isn't it? So those are both negatives, aren't they? Okay. And then you're going to have a couple other of these things. For RC. Going to have some trig in there, and you're going to have some trig and another set of moment arms. Okay. So that's what that moment equation will look like. Any questions on that? All right, so that's how I'd start that one off. Okay. Now we got, so we good on those first three? We got any questions regarding them? Doing all right. Okay. All right, let's have a look at the other three then. The other three are a little, they involve some more complex things, little different situations, you might say. So let's have a look at those. They all kind of have their little things about them to be able to figure out. They are similar in that you always start with a free body diagram and you want to get that thing dimensioned and all that so you can work with it properly. So let's have a look at that. Okay, so these things always start with a good free body diagram. That's always what you want to do with these. Okay, so what do we got? We've got the weight. Now the weight always acts down. So this is 274. And it doesn't matter which version of the book you've got. This is fine. This one's fine, okay? In both versions, it's the same problem. Okay, so you're going to have that weight going down from the center of gravity. So that's going to go down like that. And that's going to be 2,300 newtons. Okay. Now you've got some friction going on here. We got brakes, so we're going to have the friction, right? That's going to hold that thing up. And then you're going to have forces. Now those wheels are rollers, is what they are. We show the friction as one force acting there. I'll just leave it as one force, so I could do that. Then the forces on the wheels are going to be normal, aren't they? Okay, so I'll have those two forces. I'll call that RA and RB. So I'm going to start that thing off like that. We doing all right with that? We got any questions on that so far? So that's what that thing's going to look like. Now when I look at that, what I'm doing there, I'm seeing four forces. Three of them are oriented to the ramp, aren't they? So when I see that, what comes to my mind is it's going to be to my advantage to work this problem out with an inclined axis system. So I'm definitely going to do this one like that. Okay. So when you do that, the only thing you really have to deal with as far as trigonometry here is the weight. Okay. Now, the ramp is at 26 degrees, so that force will also be at 26 degrees in there. There's different ways you can prove that out, but that weight will go down at 26 degrees also. Now, there's one little thing on this that you got to concern yourself with, and this is I've kind of seen the errors people make with this, and I've made a few of them myself too. What we got, everyone always picks this component of that force up. Now that's the adjacent component, isn't it? So that's going to be cosine 26 times the weight times the 2,300. But people often forget that there's also one up there. So remember to pick that one up too. That's going to cause a moment as well, that one up top, okay? And that's going to be based on sine 26 times the weight. So you got to pick both of those up, okay? So what you would do is you got three unknowns, but if you go you're going to take moments about on that one. If you want to get two of those unknowns out of there. Some moments about what? Yeah, I go A, all right? Because you got RA and force of friction acted A. You got two of them out of the way, you can solve for B, okay? That equals 0, and then off you go, all right? So what are you going to have there? You're going to have cosine 26 times 2,300 newtons, okay? And then you see you got the dimension right there, don't you? 0.6 meters. I'm going to do that. Okay. And is that going to be a plus or a minus, that one? I think that's going to be a minus, okay? You're going to have two other terms in there. And they have RB, and of course that's the whole point of the exercise, is to figure that one out. And you're going to have another term in there too. And you're going to work through that, and you're going to get RB is 289 newtons. That's what you'll get with that, okay?
Where the tire needs to...
Yeah, thanks. That's probably worth saying. It's not at the axle, it's right there. Yeah, because that's where the friction's at. So I take it at the bottom of the wheel. Okay. So we'll call that point A. All right. And then once you've got that, keep it simple. Sum of Fx is 0. That'll get you the force of friction, 1008. And then sum of Fy, and these I should put a prime on those. Y prime is 0. And that will get you RA, which is the heavy one, because that thing's kind of tipping back on A. That's 1778. Okay. You got any questions on that one? All right. So that one's an inclined axis. I would use the x prime and y prime with that. What I would do, much simpler. Okay. Okay. All right. Here's the next one. Now this is one of those with distributed loads. Okay, and I've actually done one of these once working for a dam. You're kind of looking at the pressure on the soil is what you're looking at. You run tests on the soil in the lab and see what sort of sample, what sort of force it can take, or how much pressure it can take. Okay? And you're looking at you're kind of considering what they call the cutoff wall there for the dam to be a pin joint. And it's not a perfect way to model it, but about as good as we got. So you just go with it, right? If you're nervous, just double all your answers, right? Make everything twice as big. I don't know. It's usually not, I'm being a little facetious there, but there is that kind of aspect to it, okay? So we're going to call that a pin joint up there. And the whole thing's going to rotate about that cutoff wall. And that's a fairly common assumption on dams, okay? Okay, so what you need to do then is you need to kind of, get that free body diagram going, right? I mean, you always want to do that. So what do we got here, okay? So we're going to have a pin joint there, okay, and I show that. So what you're going to have from that pin joint, of course, is you're going to have RAX and RAY, okay? So there's two unknowns. Now the last unknown is what I'm just going to call R, and that's the reaction on account of the soil, okay? So the soil is going to push back on that floor of that dam and keep it from tipping over. That X right there. And so you're going to have R right there, okay? So there are the unknowns on the free body diagram. Okay. Now you're going to have forces acting on this thing. We've got the force, the weight of the wall and the weight of the floor. And then you also have the water load. Okay. So you're going to figure those things out. This is 17,000 here. You're given the weight of the dam wall, and then you're also given the weight of the floor, 95. And then you're going to have to figure out that water load. All right. Now you're going to want dimensions here. There's quite a few of them. So you just want to kind of keep all this stuff straight. you know, that reaction is going to be what? At the centroid, that's going to be 2/3 of the distance out from point B, right? So 2/3 of the floor distance out, because that's a right triangle for that load, and you're going to the centroid of it. That's 2/3 of 1.32, and I'm pretty sure that's 0.88 meters out. This other dimension is not. This other dimension is less than 0.88 meters. You're going to need to figure that one out right there, okay? And then you're going to need to get this one too. Again, right triangle there. You're 1/3 of the way up to 0.4, so I think that ought to be something on the order of about 0.8, right? So that's 2.4 over 3. That'll be that one, okay? So I always do these intermediate steps. I'm just not smart enough to juggle all that stuff in my mind while I'm doing a moment equation. I work it out first, then I can do the moment equation. Okay, that's how I look at it. Okay, and then once I've got that, I'll go sum of M, B, or A. Is that A? Oh, that's B there. Did I screw that up? I guess I did. Where's A? Oh, A's up top. Okay, so I got my, that should be a B right there, and that should be a B right there. Sorry. Okay, so sum of moments about B. Set that equal to 0, and then off you go. You know, you're just going to start working through that. You're going to get the 0.88 R. That'll be part of what you're going to do. 0.88 meters, and R, that's a moment. And that'll be positive. Then you're going to have minus the 9,500 newtons times its moment arm, and then minus, because it's clockwise, right? The 288, or the force of the water times 0.8 meters, right? So you're going to get all that in there, and you're going to solve for R. Now what R comes out to be is 9,743 newtons. Okay. Now what we want to know is the height, that pressure at the end. And, well, actually, it's not quite a pressure. It's an instantaneous load in newtons per meter. We want that, okay? So what we're going to know here when we work through this, in this method at least that I'm using, that I'm analyzing this with, is you've got a triangular load like that, and the area is equal to R, and I'm calling this distance here WC, the soil load at C, and then it's 1.32 meters wide, okay? So you can figure out what WC is because you know the area of a triangle is 1/2 WC times the base is going to equal R. So you can solve for WC, okay? And that comes out to be 14,762 newtons. Because what we're asked is what's the load on the soil at the end. And the design load, the governing load is at the end because that's where it's biggest. So that's the one you're going to be concerned with because that's the largest one. So if that soil's actually going to fail, it's going to fail at the end of the dam. That's where it's going to fail. Okay? And then you got to go sum of Fx and sum of Fy also on that one to figure that one out. So to finish that thing off, you go sum of Fx and sum of Fy. So with the sum of Fx, you're going to get Rbx is 2880. And then with sum of Fy, you'll get Rby is 16,757. Okay. Yes?
So, F water times distance, isn't that a 1.8?
Probably. No, actually, no, it's 1.32. I think we're good here. That one, you mean?
No, I mean,
Oh, over here.
yes.
No, because we're coming up, we're taking moments about here, It's 2.4. We're coming up a third of that. So the moment arm is there, which would be a third. Is that good? Times 2.4. All right. The F water is the horizontal load caused by the buildup of the water on the side of the dam there. Okay. Other questions on that?
So we usually have to solve for F1.
Yeah. Well, let's see. Yeah, you do, right. You have to figure out what that is. It's just a triangular load. Just find the area of the triangle to get it. Yeah, right. It's pretty straight up. Yeah, just a triangle. Yeah. All right. Good with that? All right. The last one looks like that. These things, this is kind of a crude representation, but they make these things, they have pump stations. And you don't always want to be crawling down into a pump station to pull the pump. So they make them so you can hoist the pump with a cable or a chain, and then you got a roller there that rolls down a track, and then it just kind of rotates and fits right on top of the pipe. It's kind of a slick little design. They make those so you don't have to go down and pull a pump. So you can just pull it out with a chain is the idea. Manholes are kind of dangerous places to be, so whenever they can, they like to keep people out of them. Okay, so we're going to raise the pump in and out of the dry well as shown. Okay, so this is 276, I think. Roller A rides on the track there, the vertical wall. Assume the support B is smooth. The cable is used to lower the pump at C. G is the center of gravity for the pump. So let's say that pump is in equilibrium in the position shown. Let's find the forces at A and B and in the cable. Okay, you're given the mass of the pump. All right. So what we want to do is make a free body diagram out of this, right? Now you're given the mass of the pump is 120 kilograms, but remember, we don't do statics with mass, we do statics with weight. And so the weight associated with that will be 1177 newtons. Okay. And that's just the mass times 9.81. So keep that in mind. You know, the metric unit for mass, of course, we often know, and that's kilograms. The English, the system of units we use in this country, the mass unit is a slug. Kind of an odd unit, but it's a slug. Okay, so let's get a free body diagram going on this one, okay? So what we're going to have is we're going to have the weight, and the weight acts at the center of gravity, and that's 1177 newtons. Okay. We've got this force for the cable. I'll just call that RC. You can call it whatever you want, really, but I'll call it R for reaction at C. That's a 70-degree angle. Okay. You got a roller. So you're going to have RA. And then you're going to have that smooth support there with that little semicircle. So I get if that's smooth, you're going to have RB doing that. All right. So there's the free body diagram. So we good with that? All right. Now, one thing I've told you to do numerous times is to take a moment about a pin joint if you see one, but I don't see a pin joint on that one. Okay. So we have to go back a step. Why do we take moments about pin joints? What's the purpose in that? You want to eliminate two unknowns, right? That's your purpose in doing that. So now you got to figure out where to take moments on this thing such that you will eliminate two of the unknowns. And there's a few different places you can do that, but you're going to have to kind of think that through and say, where am I going to take moments about such that I'll eliminate two of the unknowns from the equation? That's the easy way to do it. I mean, and then you can just solve for the third unknown if you do that. Now, the other thing is, if you like using matrices, and if you got a solver on your calculator, you can always just power through it and just generate 3 independent equations and plug it in and solve. I mean, you could always do that, you know. But if you want to do it by hand and solve it quick, find a place you can take moments about with that only leaves one unknown. Then come back with force equations. That's normally how the general approach. Okay? So you all got an idea where you can take moments about, so that you'll take 2 unknowns out? Yeah, just look where two of the unknowns intersect, right? All right. So find a place where you get 2 of those unknowns to intersect. You can take a moment about that. You can solve for the third. Once you've done that, you can come in and do force equations and solve for the rest. Okay. There's different places to do it, you know. Okay. All right. You got any questions on that one? All right. Questions on that? We good? Okay. So that stuff's due Thursday. Any other questions generally on this stuff? Did I give you the answers for that one? I think they're on the previous page or something. They're 2 pages back. I think these are the answers for that one. Maybe 3 pages back. There they are. Yeah, so that's on page 15. I've got the answers to that one, right? Yeah, 276. Okay, so the answers to that are on page 15. And why don't I just write them down? It might be. So RA is 300 newtons. RB is 353 newtons. And RC is 877 newtons. Something like that. Okay. We're good? Okay. All right.